So I made a video recently about using Feynman's trick to solve tricky integrals, and the truth is that I only talked about intuition in that video. I only talked about how to apply the trick to, well, solve hard problems. And today I would like to play with some rigor and maybe, proof that I could actually use it the way I did, because I'm not an engineer, for God's sake. I also have to prove stuff, and so, let's do it. Feynman's trick is a special case of the Leibniz rule for integration, which I would like to develop. I would like to prove it right now. Let's say we have a function, and let's say this function is very hard to integrate. And so we would like to use the Feynman's trick and parameterize it, well, somehow. And so we make this function a function of two variables, f of x, t, where t is the newly brought parameter. Now we integrate it with respect to the variable x, and let's just say for now that the bounds of integration are going to be dependent on the parameter t, so they're going to be a of t and b of t. And now we just call this newly made integral function I of x, t, where I stands for, well, integral. And so how will the derivative of our function I with respect to t look like? Well, by the definition of the derivative, we can express it as this limit as delta t goes to 0 of I of x, t plus delta t minus I of x, t all over delta t. And now let me just insert that integral that we, well, defined I of x, t to be inside of that limit. Also notice that the bounds of integration on the left-hand side integral got changed because, well, as t gets larger, well, a of t and b of t probably will get shifted a little bit too, so we'll change them to a plus delta a and b plus delta b. And I would like to perform a neat trick here. I would like to partition the left-hand side integral into three separate integrals. The first one on the bounds from a plus delta a up to a, the second one on the bounds from a up to b, and the third one on the bounds from b up to b plus delta b. Now I'd like to clean this mess up a little bit, so I have two integrals on the bounds of a, b. Let me combine them as such, and also I would like to flip the bounds of integration on the integral from a plus delta a up to a, because a plus delta a, well, it's probably larger, so it looks nicer. I will just multiply by -1 and flip those bounds so they look like this. And now the real trick comes into play. So how do I proceed further from this point? Well, I have to do something with those two integrals right there. Well, what can I do to them? I would like to use the thing called the mean value theorem, which states that for any closed interval a, b and any function f of x, there will be a point C somewhere between a and b such that the tangent line at C is going to have the exact same slope as the line tangent that passes through a and b respectively. That is, the derivative at C is going to be precisely the slope of the secant passing through a and b. We can write it using the slope formula as f prime of c is equal to f of b minus f of a all over b minus a, and rewrite it so that it's going to be more useful for us in the future, like this. And now let's take the first integral, the one on the bounds from b up to b plus delta b. By the fundamental theorem of calculus, we can rewrite it as this difference of primitives, just like this. But now, well, I just got to thinking, we could use the thing that we just kind of developed right there above using the mean value theorem to rewrite it as, well, let's say this thing right over there, where C is, well, the point at which the slope of the tangent line is parallel to the secant through the endpoints of the interval, which are in our case b and b plus delta b. That's pretty interesting because now notice that b and negative b will cancel each other out. We'll be left with just f of c, t delta b. But now consider one more thing. Well, since we are taking the limit as delta t goes to 0, the delta b will also go to 0, and so b and delta b are going to eventually become, well, the same number, just b. And so if c is going to be, well, between b and b plus delta b, so actually between b and b, well, it has to be equal to b. So in the limit as delta b goes to 0, this will be actually equal to f of b, t times delta b. And I love it because we can actually apply this to both of the integrals, the one from b up to b plus delta b and from a up to a plus delta a. So, well, they become those two expressions right over there, and we can just insert it back into the limit that we had earlier. So now the only thing we need to do is distribute that 1 over delta t across the entire limit. And now, as you can see, delta b by delta t will actually become the derivative of b with respect to t, just as well as the delta a by delta t will, well, in the limit become the derivative of a with respect to t. The only thing that we are, well, left to consider here is this limit of the difference of those two integrands. If we could slip that limit inside of the integral, well, then we would be pretty much done, because then we would be able to say that we're integrating the partial of f with respect to t. But can we do it? We can. And we have to use a clutter of a bunch of theorem to be able to prove it, so I'm just gonna kind of lay down to you that now is the first time in this proof that we actually will get some restrictions for f. The first one is that f has to be continuous, and the second one is that f has to have the partial with respect to t. Those are the requirements for us to be able to slip that limit inside of the integral. And so that's how our derivative finally looks like. And now we can see, well, whenever we are trying to slip the differentiation sign under the integral sign, whenever our bounds are constant, we see that, well, we will actually get pretty much just the integral of the partial, because the derivatives of our bounds are gonna be just zeros respectively, because, well, bounds are constant. And if our integral is improper, then we can rewrite it as this expression with a limit. And now if we wanted to take the derivative with respect to t of this entire thing, well, it gets a little bit tedious, because I would really want to use the Leibniz rule for integration, but I can't really do it unless I change the order of the derivative and limit operators. Can I do it? Once again, yes I can, and once again it's a clutter of theorems, but I'm just gonna lay it down to you. We need uniform convergence on the interval of integration of our integrand to be able to do this. And so, well, we actually get that whenever our integrand is convergent, we can say that the derivative of the integral is the integral of the partial. So that will be all I have to say for today. I really hope you guys enjoyed it, and see you in the next one. Bye.